plus 1 here. Today we're going to talk about trig substitution for integrals. And this is something you might see maybe in the later chapters of Calc 1, but probably more likely going to see in Calc 2 lumped together with other methods and techniques to solve difficult integrals. So what do I mean about difficult integrals? Well, I'll give you an example. So here we have the integral, a definite integral from -1 to +1 of the square root of 1 minus x squared dx. So this is a difficult integral. I don't know what the integral of that term is. If I did normal u substitution, say u equals 1 minus x squared dx, then I'll get a square root of u, but then the derivative of x squared is 2x, and so when I continue that u substitution, I have to put a 2x and a du in there, but then not all my terms are going to be used. I'm still going to have x's left over, so that doesn't work. So here's what we do instead. We look at this term and we say, okay, that looks familiar. I am going to try this method. I'm going to say that x is equal to sine of u. You could do u, you could do theta, it doesn't really matter. And so I'm going to carry over, take the derivative, dx is equal to cosine of u, and then we have chain rule du. And we can't forget limits, so we have then for our limits, for the upper bound we have 1 equals sine u, and we have for the lower bound -1 equals sine u. And so we take inverse sine of 1 and -1, and what does that tell us? That tells us u is equal to, we have pi over 2, and u equals -pi/2, right? So now we plug everything in back to our original integral. So now we have the integral from -pi/2 to pi/2 of square root 1 minus sine squared u, and then to replace the dx term we have cosine of u du. So now you're thinking, well, gee, that's even more complicated than it used to be. Well, hold on a minute. We have a trig identity, which is pretty simple one. Sine squared u plus cosine squared u is equal to 1. That's just simple trig identities. So what can we do? So that means cosine squared u is equal to 1 minus sine squared u. And would you look at that? We have that in our integral. That term is there. So let's plug it in. So we have the integral minus pi/2 to pi/2 square root cosine squared u times cosine of u du. So now what do? I see that I have a square root over cosine squared, so that's just a cosine. And we can multiply those two cosines together, so we'll have our integral as before. And now we have cosine squared u du. So I don't know cosine squared, the integral of that function, off the top of my head, but that's okay. We can just look it up in an integral table. I found it at integraltable.com, where you have integral-table.com. Really useful site. Go check it out if you're if you're needing to find various things in tables. So to get to the end of our integral here, the integral is going to turn out to be u over 2 plus sine 2u over 4. And since this is a definite integral, we have bounds of negative pi over 2 and pi over 2. So if we were, I'm going to be pedantic about this and plug it in from scratch. So that's going to be equal to pi over 4, plugging in our upper bound, plus sine of pi all over 4. Now we have my lower bound, which we subtract, but since it's a negative, we get a plus for this term, pi over 4. And then we get a minus sine of negative pi over 4. So this simplifies very nicely. Sine of pi and sine of negative pi is just 0, so both these terms go away. And our final answer becomes pi over 2. Which makes a lot of sense if you think about it. Our original function, if we could call it that, was f of x equals square root of 1 minus x squared. And if you recognize that, that's actually the equation for a hemisphere, a semicircle actually. So I could even rewrite that as y equals square root 1 minus x squared, which is actually the same as x squared plus y squared equals 1, which is the equation for a circle, right? So if we draw a graph, and if we just use the positive terms here, we have a circle of radius 1. And so taking an integral, the area under that semicircle is going to be half the area of what would the full circle be. So the area is of a circle is pi r squared. So in this case, our full area of the circle would be just pi. And in this case, half the area is pi over 2. So there you go. So you might be wondering now, how did I know that trig substitution was going to work for this particular problem? Well, there are graphs and tables for that. So you can find these tables all over. Like I said, integraltable.com is a great option. So is SOS Math. I found these particular trig substitution rules at a website, or a page rather, on Drexel University's website, but you can find them anywhere. So here are the general rules. So if you see an integral and it has the form a squared minus x squared, like we had in our last example, you can use the substitution x equals a sine theta. In our last case, a was just 1, so it was a little less complicated. So we use the trig identity sine squared theta plus cosine squared theta equals 1 to make things work. And then you can usually get a real answer for your integral. There are other forms to consider too, though. We might have the square root of a squared plus x squared, in which case we should use the substitution x equals a tangent theta. And so in this case, there's a slightly different trig identity to use. It's secant squared theta minus tangent squared same deal. And there's one more situation to consider. If it's an addition, a squared plus x squared, or x squared plus a squared, same difference. But if we have x squared minus a squared under the square root, we're going to want to use the substitution x equals a secant theta, in which case we also use the same trig identity above. But word of caution, these substitutions work under particular situations, and that's because of the different conditions of the square root and the conditions of the trig functions. So for example, for this first substitution, you should only really use it if you use this substitution for x, and your theta values, if you have a definite integral and you have bounds, your bounds stay between pi over 2 and negative pi over 2. And that's simply because if you plug in a value for theta that is less than negative pi over 2 or greater than pi over 2, you're going to get a negative number underneath the square root, and that's a big no-no. Technically in mathematics you can do that. It results in an imaginary number, but for integration you don't really want to deal with imaginary numbers. It just doesn't work. You kind of want a real scalar value as the result of your integral. And same for the other substitutions. For the a squared plus x squared, square rooted, you want to stay between negative pi over 2 and pi over 2, but you cannot equal either of those values either. And that's because in this case you can kind of have any number that you want underneath the square root. It's always going to be positive because everything is squared. The problem is that if you plug in pi over 2 or negative pi over 2 for your secant or your tangent, you're going to get an infinity, and normally that's not a good thing, especially for an integral. And so your last substitution has two different stipulations. So if x is greater than or equal to a, then your theta should be between 0 and pi over 2 for a combination of the same reasons above. And if x is less than or equal to a, then your theta should be between pi over 2 and pi. So that was a pretty easy example, our first one though. We could even check it just by looking at a graph and saying, yep, it should be pi over 2, makes sense. But what if we have a more difficult integral to look at? So for example, let's say we have the integral, this time it'll be an indefinite integral, the square root of 9 plus x squared dx. So in this case, just as before, we can make a trig substitution, but we have to be careful with our constants here. So in this case we have an x, we also have a, which is equal to 3, since 3 squared equals 9. So I'm going to, from the table before, make the substitution that x equals a tangent theta, which is equal to 3 tan theta. So what happens to the integral then? Well, hold on. We need also the dx, which if we find the derivative of tangent theta, we find it's secant squared theta, and the 3 just carries over. And of course we need a d theta with the chain rule. So plugging back into our integral, we have square root of 9 plus 3 squared tangent squared theta, and then we plug in our dx. 3 secant squared theta and a d theta. So it looks a little ugly, but don't worry. Again, it'll work out. So I'm going to pull that 3 out since it's just a constant. So we have 3 times the integral, and now I'm going to simplify this square root a little bit. So I know that 9 is actually 3 squared, and I also have a 3 squared here. So I'm going to pull out the 3 squared, and we're going to have the term 1 plus tan squared theta. And of course we still have the secant squared theta and a d theta. So I look at that and I say, okay, this is good. I can pull out the 3 squared because square root of 3 squared is just 3, and I'll pull that out of the integral. And using my trig substitution, or rather my trig identity, I can replace 1 plus tangent squared with a secant squared. So let's rewrite this. So we're going to have 3, which is already out, times 3, this 3 that we pulled out of the square root, times the integral of, let's see, square root secant squared theta times secant squared theta d theta. So we're getting there. So let's simplify some more. The 3's combined to make a 9. Our secant squared under the square root just becomes secant, and we can combine these terms to make secant cubed. And so now we're kind of stuck. Yeah, who knows what secant cubed is as an integral. Well, again, this is one that we have to look up, and it's kind of messy, but it's an answer. So we have our constant 9, and now we have the answer, which the integral of secant cubed is 1/2 secant times tangent. But don't worry, it's not done yet. Plus 1/2 natural log of the absolute value of secant theta plus tan theta. And that's your final answer right there. It's a little long, but it's not too unreasonable. It would be uglier if you had a definite integral with limits and you decided not to alter the limits and just plug in your theta equals whatever u. It would be pretty nasty, but if you change your limits to go with theta or whichever substitution variable you use, it'll look a little better. So there you go. There's a overview of trig substitution. I hope this helps, and good luck.